Presented by Caltech.
So the first speaker this afternoon is Lars Bildsten from KTP, and yesterday he gave us some advice. Now he will tell us about some science, and Sterl Phinney will introduce him.
So last night, John Preskill emphasized the importance of being a two-trick pony. But I'd like to use Lars Bildsten to illustrate another approach to career success besides being a two-trick pony. That's the process of taking inspiration from your environment. And I hope I'll also convince you that this is an exciting new field of meta-analysis, perhaps more interesting than the use of citation statistics and H-indices and collaboration network graphs, the Freudian psychoanalysis of publication titles. So Lars grew up in the Midwest and got his bachelor's degree in engineering physics from Ohio State, and then went to Cornell for his PhD, where he worked on sort of straightforward nuclear astrophysics problems. But then he came to Caltech as a prize postdoc, and the inspiration from his environment clearly began. So while he was here, he got to see the Pacific Ocean, he got to see the tides go up and down, and the spectacular forest fires in the mountains. So the papers that he wrote while here have titles like Tidal Interaction of Inspiraling Binaries, Non-Radial Oscillation of Neutron Star Oceans, Propagation of Nuclear Burning Fronts, and my all-time favorite, Rings of Fire, the Flammability Limit, and then how nuclear burning fires spread on neutron stars. So then Lars moved to UC Berkeley, and you all know the reputation of Berkeley students and politics. So Lars was inspired to write papers with episodes, outbursts, torque reversals, and lithium depletion in young stars. Then he moved to KITP in Santa Barbara and had a walk around Isla Vista, I guess, and noticed all the people with the shopping cart. So he has papers on transient neutron stars, the transient universe, unstable non-radial oscillations, and arresting accretion torques. Then there were the earthquakes, so seismology and accreting white dwarfs. Then there were the fires where his neighbors' houses burned down, but fortunately his didn't, so ash exposure and X-ray bursts. And then, of course, he had to get into fundraising for KITP and his daughter's school, so there's hot white dwarf donors and other donors-type stars. But finally, there's another part of his environment, which was this retired guy from Adobe who came into his office and wanted to do something in astronomy, Bill Paxton. So together they've transformed the field of stellar astrophysics from one which, at least when I was young, was sort of passé already by the early 1980s, into a really vibrant field that lots of young scientists are piling into. And they did it by making open all the problems that the giants of astrophysics has swept under very thick rugs of proprietary code in the 1950s, 60s, and 70s, and creating an open source code. Now, to understand the Freudian analysis of this, you should know that UCSB is on a MESA, and the road past Lars's office is called MESA Road. So inevitably, their revolutionary open source software are called Modules for Experiments in Stellar Astrophysics, or MESA. So Lars has been a great colleague, friend, and collaborator for me and for many of my colleagues at Caltech for the last 25 years. So, Lars.
So everything he said is true, except Bill Paxton named it for MESA for some other reason. I can't remember which, but we have to ask him. So what I want to do today, this afternoon, is indeed talk about what's happening in stellar evolution. And I'm really going to focus on one particular problem because it's something where the Kepler satellite is just giving us tremendous data. So that's the main focus of this talk. And the main issue is that we can now really probe the interiors of stars. So the prime change we've had in the last 5 years is that we now have observations, in particular astroseismology, that allows us to really understand what's going on in deep interiors with direct measurements as opposed to inferences. Prior to that, there wasn't a lot you could learn about a star in our galaxy other than measure its temperature, its luminosity if you know its distance, surface gravity. But now we can really understand the deep interiors. And that's allowing us to ask new questions about rotation, how rotation evolves, but also to differentiate the state of the core of a star independent of knowing what the state should be, because as I'll show you, some stars are at the surface nearly indistinguishable, but the core can be extremely different. And there's many people I've been doing this work with, and they're all listed here. Some of them you may know. Matteo Cantiello is a postdoc at KITP. Jorn Christensen Dalsgaard, sort of one of the fathers of the field of astroseismology, really did most of his work on the sun. Jim Fuller is a postdoc here and spends some time at KITP. Two undergraduates who were with me in Santa Barbara now are at Santa Cruz, Phil Macias and Chris Mankiewicz. Grad student Kevin Moore, and then Bill Paxton, who I'll talk a little bit more about. Dennis Stello, who's a Kepler observer, and Rich Townsend, who's written an amazing open source code as well called Gyre, which does fully non-adiabatic stellar pulsations. So since I'm sure all of you took stellar structure, but it's maybe been so long ago you don't remember, I do need to remind you a little bit. So on the left is a diagram in theory units, so at least I've spared you from the astronomicals. This is the luminosity, the log of the luminosity of a star in solar units. On this axis is the surface temperature. These are stellar evolution tracks from the MESA code. This is a one solar mass star finishing its hydrogen burning, going up what we call the red giant branch till it gets to what's called the tip of the red giant branch, where something dramatic happens in the core, which I'm going to talk about, which is this ball of degenerate helium, which is nearly half a solar mass, gets dense and hot enough to ignite and start to burn, and it's actually unstable and has a series of unstable flashes. And when it does that, it somehow finds its way back to a region where it sits for about 100 million years undergoing helium burning. So the first phase of the main sequence is hydrogen burning hydrogen to helium. The second phase is burning helium to carbon and oxygen, and that occurs when the star is sitting about here. On this side is a different plot. This is showing the central temperature and the central density of the point right at the center of a star as a function of time. So again, here it's leaving, this is on the main sequence. It's burned its hydrogen to helium. It then undergoes contraction. You can see its density goes up nearly a factor of 1,000. Becomes degenerate. This is the line of degeneracy. To the right of this line, the Fermi energy is more than 4 kT. So the electrons are becoming very degenerate. Goes up till it ignites helium, and I will talk about this much more. And then through about 2 million years of flashes, lands up here sitting on the helium burning main sequence. Now, as Sterl mentioned, one thing we have been doing is reminding everybody of what's known, but more importantly, allowing everybody to play in this game. And most importantly, because it's open source, you really can enable a lot of people to do experiments, and that's what the E is in MESA. This understanding of this helium core flash was done in a beautiful paper by Thomas in 1967. The only problem with that paper is that it was in German. And unfortunately, that means that most people didn't remember it, and so I'm going to spare you all the textbooks which misstated the mysteries of this problem, and it's because they just hadn't read the literature. But what I want to talk about today is we can now start to probe this transition I've talked about through astroseismology. And that's what is a very exciting opportunity for us. So that's happening because of two satellites that were launched. The first was Corot, which was primarily a French mission, which was an optical telescope 27 centimeters in diameter. And then the one that really I'm going to emphasize today is the Kepler satellite, which is, again, a roughly 1 meter telescope in space. By going into space, you don't have to deal with the atmosphere, and so you can measure the brightnesses of stars and the accuracy of the brightness of stars, only limited by the Poisson statistics of the photon counting. And that's allowed for measurements of brightness variations down to about 10 parts per million for 10,000 stars. And if a star is ringing and oscillating, you can detect it, and that's what I'm going to show you. So first I have to give you a sense of how stars oscillate. If I just write down a local dispersion relation for a wave that's traversing through a star, there's really two parameters that matter. This is the radial wave number. Omega is the oscillation frequency that I'm considering. And there's a local frequency which we call the Lamb frequency, which you can see is the sound speed divided by the local radius. L is the angular for the YLMs, because we're doing for now, we're presuming the star is spherical, and we're also presuming for now no rotation. I will talk about rotation. But the first type of modes you can get out of this dispersion relation are what you know and what you're hearing right now, which are acoustic waves. Literally just standing acoustic waves in the star, which as you add more and more nodes between the surface and the core, the frequency rises. So that you're very familiar with. So that's evenly spaced in frequency, and these primarily, as I'll show for the giant stars, we're talking about live in the envelope, and that's the dispersion relation in the high wave number limit, which is just what you know for sound waves. However, in stars, there's one other type of oscillation that's possible, which is an oscillation due to the fact that if I take a fluid element within the star and I push it up, it can be denser than the surroundings and bob back down. There's therefore a local restoring force, and that local oscillation frequency is what's called the Brunt-Weissler frequency. That's this big N squared. And that tells us about the properties of the star. So you don't think about these waves maybe quite as often. In the Earth's atmosphere, we have them. In the ocean, deep in the ocean, you may have them due to salt gradients, but since water is nearly all the same density, there's almost no buoyancy, so it's a very low frequency. But stars have this if they have a stably stratified part. And if you do the WKB for these waves, which are unfortunately, and confuse people, also called gravity waves, they're not gravitational waves, have a dispersion relation where they'll be evenly spaced in period rather than in frequency. And I'm going to show you detections of both of these now in these red giants. If I plot these up for the sun, which is really where this field started and where really our understanding of how to do both the theory and the observations had its early start. This is a plot showing the Lamb frequency. Remember that's CS squared over R squared, so it's diverging at the core because of just the 1 over R squared. So this is the Lamb frequency. This is the Brunt-Weissler frequency in the sun. Out here is a convective envelope. This is the radius of the sun is 1 is the surface here. Here's the core. And so the outer part has a convection zone, and in that convection region there is no support of the motion of the fluid. If you lift it up, it's the same as its surroundings, more or less. And so there is no restoring force, and that's why this crashes to 0. Acoustic waves come in, and this is a turning point. So these waves will come in, and they'll turn. This is for L equals 1, L equals 2, L equals 3. And so how deep they penetrate into the core depends on what the angular momentum is of the wave, or really the angular wave number. So this is the sun. In the sun, acoustic waves have been observed for a long, long time, and I'm not going to talk about it. So let's talk about giants. Giants, as I showed you back here, are these objects, something like the sun that's left the main sequence, has this degenerate core of helium that's very dense and a big puffy envelope. And as it rises up, this is, as you see, constant temperature, the luminosity is increasing, so the radius is growing dramatically as it goes up the red giant branch. And if I do the asymptotics of an acoustic wave in a star, you can show that they are uniformly spaced in frequency. And this delta nu, this frequency spacing in the WKB limit is roughly this integral, which is a measurement of the mean density. Because this is the integral of the sound speed, and the star is under hydrostatic balance. And so you can show that the frequency spacing will give you the mean density of the star. So for red giants, prior to Kepler, there were maybe only 4 or 5 that have been observed to be pulsating due to radial velocity studies from the ground, and maybe 1 or 2 from space from sort of specialized observations. And so the pulsation amplitudes were estimated based on work that actually Peter did for the sun, but these ground-based tests were a challenge as the amplitudes were actually quite low. So I wasn't around within the Kepler team or really connected to this at the time, so I don't know if they were expecting success or not, but this is really an offshoot. Remember Kepler, you've probably all heard for its other stuff, which is finding planets. This is the other part of the Kepler mission that you may not have heard about. So Kepler didn't get there first. This other French mission got there first. It found all these acoustic waves. They studied about 300 giant stars. Every one of them showed acoustic waves, and they measured the mode lifetimes to have a lifetime of about a month. So this appeared in 2009. Then Kepler did it very quickly as well. And this is now showing the power spectrum on this axis. These are different stars. Ignore the numbers. That's just the the target number for Kepler. This is frequency in microhertz. And so what you can see immediately is different stars have different maximum frequencies, but you might already start to see there's some uniform spacing going on here. You can fold it, and this is the original betting paper from Kepler. You can fold it for different objects, and then this is basically the radial number. This is n, and you can see these distinct spacings in frequency, and it's roughly n of 10 to 15 typically. So this is really quite remarkable. You can see L equals 0, L equals 1, L equals 2, and sometimes even L equals 3. And I'm sort of not showing you all the data. Keep in mind, this is from seeing the brightness variations. So when the waves get to the surface, they change the temperature a slight amount, and that's then the brightness variation that's observed. You'd expect as you go to high L, the integration over the disk of the star, you'd start to have a drop in the amplitude observed just due to the cancellation. And indeed, L equals 3 is as high as has been seen. But that's still fantastic. So now, with Kepler, there's about 10,000 stars for which I could show you power spectra like this. And this gives the mean density straight away. Well, it keeps going. If I go back 2 slides, there's another thing that's characteristic in the power spectrum, which is that, let's just take this one because it's easy to see. You notice that even though there's sensitivity to higher frequencies, there's absolutely nothing here at high frequencies. There's a typical frequency of maximum power, and you can see that's how they've stacked these intentionally. Okay? The question is, what's the origin of that? Well, the understanding of that was already expected, and is that the highest frequency is roughly what's called the acoustic cutoff. So the way to think of it is it's a standing wave within the star, but as it approaches the surface at a fixed frequency, because the sound speed's dropping, omega CSK, the wave number is getting really high, or the wavelength's getting very short as it approaches the surface. And there's a characteristic wavelength at the surface then, which is of order the local density scale height. And at that point, the wave is either going to see it as a reflecting or a transmitting boundary. At high frequencies, it's a transmitting boundary, and so the wave is very leaky. And therefore, the hope/expectation is that the higher frequency waves have shorter damping times, and therefore they never get to large amplitude. So it's quite remarkable how well this has worked. This is a really busy diagram on the left that just tells you there's a hell of a lot of stars for which they've measured them. This is like the diagram I showed you, but now they're plotting the maximum frequency. And for larger stars, the maximum frequency is much lower. It's a bigger pipe, if you will. And this works extremely well at inferring then from the objects little g. You measure the sound speed at the surface because you have an effective temperature measurement. But this formula, which is the phenomenological formula and has been checked in binaries where you actually have the mass and the radius separately in eclipsing binaries, does work to about 10%. And so the first thing that happened just from the acoustic waves was measuring the mean density, m over r cubed, and measuring log g, little g, gm over r squared, and that then gives you m and r independently. So again, for 10,000 stars in our galaxy, they don't have a mass and a radius. And that's profound and has big impact on galactic structure, understanding how the Milky Way's been built, because this is the sort of data you can't typically get. And it will be tested beautifully by Gaia. They also think they know the distances. Gaia is going to measure the distance. So this will be a wonderful opportunity for learning more. But these waves, not unlike in the sun, are acoustic waves that only penetrate so far. Okay? And so all you're really getting are these mean measurements of the mass and the radius. So let me talk a little bit more about what happens in the last sort of 100 million years of a star's life as it goes up the red giant branch. So this is one solar mass star rising in time going this way. This is about 60 million years before it gets to this tip, 30 million years. This is the tip of the red giant branch where the helium core flash occurs. And then this is coming back down, and then it sits here and burns helium for a finite time. The problem to the observer is that we don't know typically for a star in our galaxy what the mass truly is, and the surface temperature measurements aren't always so great, and so therefore it's really hard to distinguish whether a star in this luminosity regime is going up or is one sitting here burning helium. So to the observer, it's the same surface temperature and same log gravity, but one of them has a degenerate helium core that's very compact and is not doing burning, and this one has a much puffier helium core that's undergoing helium core burning. So the state of the star is completely different, but you wouldn't know from the outside. And this is where things got quite exciting in the astroseismology. So let me show you for a star that's going up the red giant branch what this propagation diagram looks like. So again, this is the radius of the star on this axis. This is showing what's called the Lamb frequency. That's the CS squared over R squared. L equals 1, L equals 2. The core of this object does support waves, so it does have a finite Brunt-Weissler frequency. That's this black line. And what was done in the 70s by theorists was realizing that a wave that comes in should get reflected here, but there's a finite tunneling probability, and if it could, it would then oscillate in the interior. So between this point, here, and here, this region is evanescent. If you just look at the dispersion relation, is an evanescent wave, but you never know. Maybe it would have enough amplitude to probe the core, in which case you'd actually measure the information on the core. Okay, so this had all been done theoretically. The coupling should be strongest for L equals 1 because the L equals 1 evanescent point is here. Here's L equals 2 is here. So you'd expect to see it first for L equals 1 because the penalty of the WKB damping is less for this one. Now, of course, I wouldn't be showing you this if it didn't happen. And so here's probably the best case to show. And these are data for two different stars. They're basically two stars. One is going up the red giant branch, one is adjacent to it, is burning helium. They're almost identical in their radii and sizes. And so things like their mean, they both have 8 microhertz delta nu. That means they have the same mean density. They almost have the same maximum frequency. So in terms of mass and radius, they're nearly identical stars. And what you can see here, so this is L equals 0, L equals 1, L equals 2, and then it repeats. You see 0, 2, 1, 0, 2, 1. This is the frequency spacing. But if you look around L equals 1, you will notice there's other stuff. L equals 1, there's other things. Down here, L equals 1, there's other things. Nothing around L equals 0. That's a radial mode. There is no radial gravity wave, and so L equals 0 has no splitting. L equals 2 has almost nothing. And you might also notice that these have different period spacings than those. So this star, we know now, is a red giant branch star that's going up, and this is a star that's doing core helium burning, and you can see directly the period spacing being completely different. Okay, so this just popped out. So let me show you what these look like if you do an eigenfunction calculation. This is a sort of a shameless plug for Rich Townsend. So Rich has this open source code called Gyre. And so these are from him showing two different waves. So again, at the surface, they're both acoustic waves, and you can see 1, 2, 3, 4, 6 or 8 nodes. So they're acoustic waves. But in the core, they're very different in amplitude. It's hard to see on this plot, but they have different amplitudes in the core. One is what we call a P-dominated mode. It's roughly an acoustic wave. But in the core, it has 476 nodes. It's very low frequency. So we can really do WKB with confidence. That's great. One of them is a G-dominated mode with a higher order, 500 nodes. So these waves really are living in the core and manifest themselves at the surface. And that WKB penalty is only about a factor of sort of 2. It doesn't kill you too much for the ones we see. There are others where we never see them, and we understand that as the waves are damped. Not damped, they just don't couple. So Tim Benning had a paper in Nature showing this, and I'll explain this plot. So as a star goes up the red giant branch, it's in this direction. So that's radius is increasing. Frequency spacing is decreasing. Again, it's getting to a bigger pipe organ. And then what he's showing here is this period spacing of the core G modes. That's these points. Okay? That's the blue points. If it's undergoing core helium burning, the period spacing is completely different, and it sits here. So these two populations just absolutely distinguish themselves, just fell straight out. Here's the same thing from Corot. Basically the same bit of data. So when this came out, this got me quite excited. because for many years we've never been able to do this. You can now point to a star and say what's going on in the core, and it's really quite profound. So what I want to close with is how does this electron degenerate helium core transition to this burning state? And as I already said, we think through a series of thermonuclear instabilities over a rather long time period, about 2 million years. And as I said, it's overlooked and never tested. We haven't been able to test this prediction of stellar evolution. So there's Bill Paxton. Sterl already mentioned him. He indeed is, well, I can't say he's retired. He works harder than anybody else I've ever worked with. But he did PostScript, for those of you who are old enough to remember PostScript, before it became Adobe, and then left Adobe pretty quickly because he doesn't like working in big groups. And wanted to do something different, and since then we've been working, and this is the first paper we wrote. There's a number of us who've been working with him, and now there's about 700 users. And this is an open source stellar evolution code that really lets you test, hypothesize, and more importantly, really allowing the community to do new things. So I'm going to show you what happens in a helium core flash. And this is sadly no real different than what Thomas did, except we can really do it more easily today. So here's the temperature profile in the helium core. So this is density on this axis, temperature on this axis. This is the helium core, the black line pre-flash. Okay. Outside, there's a hydrogen burning layer sitting right here. That's hydrogen actively burning, making the helium core grow in mass, and because it's a degenerate object, shrink in radius. Again, it's about a 0.5 solar mass helium core. And what you see is that the helium flash starts off-center. Does not start at the center. Starts off-center. So 40 years after, sorry, I'm doing this wrong. So pre-flash, 40 years before the maximum temperature, this is the time scale is 40 years. It gets from here to here, and the flash proceeds. And this is in mass coordinates at a frozen location. So all this expansion you're seeing, the core undergoes an adiabatic expansion. The shell is ignited and lifts up. And so the core just undergoes adiabatic expansion and cooling. And the surface gets pushed out, undergoes adiabatic expansion. You shut off the hydrogen burning. And this happens on a fast time scale. And this is one of the reasons people were worried about whether it's a hydrodynamic event, is the time scale. You see, here's a case from here to here is in 20 days. So you typically don't think about stars evolving that rapidly, but that's what you find in this case. We still don't think this is hydrodynamic. The time scale for sound waves to traverse the core of this object at this density is 10, 100 seconds, nowhere near, maybe even 1,000 seconds, but nowhere near this time scale. So we're not too worried, but you really want to test it, and that's the whole purpose. Well, one immediate prediction that was in the Thomas paper, and one that I know some people are now looking for, is when I push this hydrogen burning layer out, the hydrogen burning shuts off. And if I shut off the hydrogen burning, that big giant envelope loses its luminosity source, and it just undergoes gravitational contraction. And that's shown here in this plot. This is the radius of the star as a function of time for different objects, and these are just undergoing what's called Kelvin-Helmholtz contraction on a time scale of 100 to 1,000 years. They just come crashing right back down. And this is another prediction of this, of our understanding is that one should find, and it's a hard problem. They take 100 million years to get up, and they take 1,000 years to come down. So they're rare, but I do know some people are looking for them. And then this is a mess. I just wanted to show you to impress upon you that we're not just making stuff up. What's weird about this core flash is it's one of many. And what's shown here are successive flashes. These are just the location and mass coordinates where the flash is occurring. And basically, after the first flash, you have to wait for a while. Heat goes in via thermal conduction in this degenerate electron core. And as the heat goes in via thermal conduction, it ignites another flash. And so this time scale is 2 million years. And that is the time it takes for the object to get itself into the state we would expect it to be, which is a helium-burning core, which is here. And so this is the time scale over which the core is really unusual. It's not the core you'd expect. It's still undergoing flashes, and so that's the seismology we want to probe. Now you might say that's a hard problem, but it's actually not when you have thousands of stars. So If I go back to this slide, this jigging up and down is actually during this 2 million years, a little bit of it is. But the stars here, in terms of how many are within Kepler, is about 5,000 clump stars. And they spend only 100 million years there, and for 2 million years, they're unusual. So we're talking 1 in 50 stars. So we should be able to identify them, if, again, this theoretical understanding is correct. And again, for the aficionados, this is what these cores look like. So this is the only curve worth looking at. This is at a typical time. This is the hydrogen burning layer that's now totally turned off. It's a density jump because of the hydrogen-helium transition. This core has a really bizarre temperature profile, so that's the Brunt-Weissler frequency. And therefore, this has a completely different period spacing than either two cases. And that's the prediction we made 2 years ago, is that there should be 2 million years, the thermal time through the core. 1 in 50 stars should be an unusual state. And there's 5,000 giants, so things should start to emerge. So just not that long ago, another paper came out from Kepler, where at least they're reading our papers, because they took the stars that weren't falling where they should, and they called them flashers. So at least they're aware. But what I haven't seen yet is I need to really look at the actual Fourier transforms for these objects, which I haven't seen yet. So they're starting to identify outliers, but you can see it's really clean. It's quite remarkable how clean this really is. And you can see how easy it is to distinguish the two. OK, so in the last few minutes, what I want to talk about is the next thing that is emerging is the measurement of rotation. So again, since all of you took stars so long ago, I need to remind you of how this works. So the sun is rotating roughly at 30 days. And for this talk, I'm going to assume it's a rigid rotator, because I don't need to worry about the slight differentials. So here I am, the sun rotating at 30 days. Each of these lines is showing a trivial calculation, which is I just take that fluid element and I assume it conserves angular momentum. And I just ask, how would its rotation rate evolve? OK, so the core contracts and the envelope expands. And so these points, which are the inner 1%, 5%, 10%, 15%, all undergo contraction and therefore, naively, rapid spin up. Whereas the outer envelope expands and would spin down. And if I assumed the whole thing was just a rigid body, I'd have the dashed line. The point is, stellar evolution naturally leads to creating a huge amount of differential rotation. So the question is, what's the star do? Well, we can start to probe that because in Kepler they're seeing rotation, rotational splitting. So this is a blow up now of a, as they say, a typical case, right? Haha. This is just one star. Here's L equals 0, L equals 2, L equals 1. So this is the radial. This is L equals 2. The L equals 1, as I already talked about, is split. It has P modes. Here's the G modes, here's a G mode, here's a G mode. So this is the acoustic wave. These are the core G modes. The first thing you may notice is these core G modes are nearly pure tones. I didn't say that before, but I should have. The core G modes have extremely long damping times, and they're actually behaving much like clocks. And that's going to be another interesting thing for Kepler to use, is to use those as clocks to maybe discover things that are orbiting the star, like you would for radio pulsars. So, but what you may see, this is L equals 1, and you see this is split. So this is split into a triplet. There's a triplet, triplet, triplet. And so this is measuring the core rotation. This mode, the P mode, primarily lives in the envelope. It has a slower splitting. But you see that we're directly measuring now the rotation of the star. Okay? So again, you do that for many stars. And this is now as a function of radius. So these are, ignore the lines, okay? Just look at the data. These are then red giant branch stars going up the red giant branch. And you can already see that they're spinning at 10 days up to 50 days. Then there's no data. And then the star comes back, and it's a helium burning star. And now it's rotating at about 100 days. Okay, so these are all measurements. That's where the measurements sit on this plot for the core, 10 days. If it were conserving angular momentum, it would be rotating 100 times faster. So these objects are losing roughly 95% of their angular momentum. You can take all of any or all of the current models for angular momentum transport that are used for all of stellar evolution, tweak them to your heart's content. You can never get that data point. So we have a problem, which is that all of our current understanding of things that are, even including magnetic fields, do not translate to this problem. And so, and that's what this plot is showing. This is work that Matteo Cantiello did. So here are the data. This is if you presume it's a pure fluid, which none of us would do anymore. That's nearly constant spin-up. This is with what's called Sprout-Taylor dynamos, a recipe that's used for massive stars. Because people want to get angular momentum out of massive stars so they can get the core to collapse. That's not efficient enough. And so basically there is no current model that gets you these slow rotations in the core. So somehow these objects are losing angular momentum at a much more rapid rate. So let me just conclude to say these tools are really telling us new things. We're just starting to do rotation. And as a theorist, I think it's really important to say we remain key in 3 ways. One is we're really helping because we can do reliable physical modeling, needing to interpret the data. There's novel analytics and mechanisms. Jim Fuller's got a nice paper with other collaborators on a wave transport mechanism. And we're really suggesting new ways to look at data to reveal rare physical states. So thank you.
Yes, in the back.
Kurt.
Have we learned anything about magnetic fields for these measurements?
Not yet. Not yet. There's some indications of weird objects for which you may want a magnetic explanation, but it's early days. Yeah.
Lance?
Looked like there was a small splitting of the LJ0 node on the far right. What causes that? Those wings on the far right.
This is the radial mode, so this better not be rotationally split. And typically, there's always a little bit of hash on these, so these have short lifetimes. So one question is just how, what is this, I don't know the duration of this Fourier transform, but these typically have lifetimes of 30 days. So what you could just be seeing is the Q. But I don't know specifically for this object.